All of this incredible AI that's suddenly everywhere, ChatGPT, the way Google search works now, all of it? What if I told you that almost all of it can be traced back to a single revolutionary idea? An idea from just one research paper that really quietly changed everything. Okay, let's get into it. This is it. This is the paper. It was published by a team over at Google back in 2017. And that title? Well, it's not just a title, it's a mission statement. An incredibly bold, almost crazy claim to make at the time. Attention is all you need. See, this was a radical idea. It was basically proposing we throw out all the complicated, slow methods that AI had been relying on for years. And it turns out, that radical statement, well, it became the blueprint. The architecture they laid out, which they called the transformer, is the engine behind this entire generative AI explosion. It's literally the T in ChatGPT. It's the reason these models can understand and talk like a human. So here's the bottom line. If you really want to understand how we got here, you have to understand this paper. But to really appreciate the genius of what they did, we first have to talk about the huge problem they were trying to solve. Before this paper, AI had this massive bottleneck, especially when it came to understanding language. So the old way, using models like recurrent neural networks, was sequential. I want you to imagine reading a book, but only one single word at a time. That's pretty much how these models worked. They'd read the first word, think about it, then read the second, and so on. This was not only super slow, but they'd often kind of forget the beginning of a long sentence by the time they got to the end. The new way this paper introduced was parallel. It's like going from reading through a tiny straw to just opening your eyes and seeing the entire page, every word, all at once. And this table from the paper shows you that bottleneck in black and white. Look at the recurrent row. That's the old way. See where it says sequential operations required is O of n? That just means the longer the sentence, the more steps it takes. It gets slower and slower. Same for the maximum path length. It was hard to connect the first word to the last. Now, look at self-attention, the new way. Both are O of 1, constant. It doesn't matter if the sentence is 10 words long or 1,000 words long, it can connect them instantly. This wasn't just an improvement, it was a total game changer. So how in the world did they pull off this massive leap from one word at a time to seeing everything at once? They did it with a single, incredibly elegant idea at the heart of their model: attention. Or, to be more specific, self-attention. Self-attention is the secret sauce. Here's what it is in simple terms. It lets the model look at a whole sentence, and for every single word, figure out how important every other word is to understanding its meaning. It just weighs all those relationships at the same time. So if you have a sentence like, "The delivery truck blocked the driveway because it was too wide," self-attention is what helps the model instantly know that it refers to the truck, not the driveway. It just gets the context instantly. Now, this powerful new idea of self-attention needed a home. It needed a brand new architecture designed to let it do its thing. And that architecture, they called it the transformer. At its core, the transformer has a pretty straightforward two-part job. First, you've got the encoder. Its only job is to read the entire input sentence, let's say a sentence in English, and build a super rich understanding of its meaning. It gets all the context, all the relationships between words. Then there's the decoder. It takes that deep understanding from the encoder and uses it to generate the output, one word at a time, in, for example, German. One part reads, the other part writes. But they didn't just use one layer of this self-attention. No, they used something called multi-head attention. And this is just brilliant. Think of it like having a committee of 8 experts all reading the same sentence. One expert is just focused on grammar. Another is looking at who's doing what to whom. A third is just tracking what the pronouns refer to. Each head is one of those experts, looking at the sentence from a totally different angle. And by combining all their insights, the model gets a much deeper understanding of the text. Okay, but this created a new problem. If you're processing all the words at the same time, how does the model know their original order, right? The dog bit the man means something very different from the man bit the dog. Without word order, it's just a jumbled bag of words. Their solution was super clever: positional encoding. Basically, they add a little bit of math, a unique signal, to each word that tells the model exactly where it was in the sentence. It's like taking a shuffled stack of pages and adding page numbers so you can put them back in the right order. Okay, so the theory is elegant, the architecture is clever, but did it actually work? Let's look at the results. Because they weren't just good, they were absolutely jaw-droppingly stunning. This table right here is from the paper's results, and it compares their transformer model to the best of the best at the time on a standard translation task. The score they use is called BLUE. All you need to know is higher is better. The previous state-of-the-art, which was actually a bunch of different models all working together, maxed out at a score of 26.3. The single, elegant transformer model, all by itself, just blew right past it, scoring a 28.4. Now, a jump of 2.1 BLUE points? That might not sound like a lot, but in the world of machine translation research, that is a massive leap forward. It's not just a small improvement, it's a genuine breakthrough. This was the moment everyone knew a new era was starting. And here is the real kicker. It didn't just get better results, it did it using way, way less computing power. This chart shows the training cost. The transformer got its new state-of-the-art score using just a fraction, about 12% of the computational power of the older models. So it was better, it was faster, and it was cheaper to train. That's a trifecta you almost never see. So what happens next? Well, when you have something that is better, faster, and cheaper, it doesn't stay locked away in a research lab. It explodes out into the real world. And that's exactly what happened. The transformer architecture became the foundation for pretty much all modern large language models. As we said, it's the T in ChatGPT, but it's also in the models from Google, from Anthropic, from every major AI lab. It's the engine behind huge improvements in search, in translation, and now it's being used for things way beyond text, like understanding proteins in biology or generating incredible art. Its legacy is literally everywhere you look in AI today. So it all comes back to this one paper with its audacious title that gave us the key. It proved that by allowing a model to just pay attention to everything at once, you could unlock this whole new level of intelligence and efficiency. And it leaves all of us with a big question. If attention was the secret ingredient that got us here, what's the next revolutionary idea that's going to take us to whatever comes next?